we will wait, let's say, 1 additional minute before we start with the actual event. All right, I think we can slowly start. More and more people are dropping in, but therefore I make the introduction. Yeah, welcome everyone to the first Young Minds Groningen event of the new year. Today is the International Day of Women and Girls in Science, and therefore the event today will focus on the gender equality in science. It's our pleasure to announce that we have 4 renowned female scientists as our speakers today, including Professor Irene D'Amico, Professor Ivonne Albuquerque, Dr. Francesca Primas, and Dr. Tana Joseph. We are very happy that we can draw the attention of our scientific community to such an important topic. Gender equality in science is or should be the goal of every researcher, and not only for women. And we hope that we can further promote this goal of gender equality in science with our event today. All right, before we start with the actual event, I would like to briefly introduce ourselves. So we are the EPS Young Minds Groningen. EPS stands for European Physical Society, and that is a non-profit organization that promotes physics within Europe. EPS is consisting of 42 member societies and has 3,200 individual members, and therefore it's representing more than 100,000 European physicists. The Young Minds is a project started in 2010 by the European Physical Society as a platform for students and early careers researchers in physics. So there are many different Young Minds sections existing within Europe. Some of the locations indicated on the map here on the right, and we are representing the Young Minds Groningen section in the Netherlands. So the main goal of the Young Minds is to encourage leadership in young researchers in physics, to foster physics among local communities and institutions, and to connect young scientists in Europe. We, as the Young Minds Groningen, are currently consisting of 11 members from 9 different countries. So I would argue that we are a quite diverse and open group. And in case you are also a young physicist in Groningen, please feel free to contact any of us. We are always happy to welcome new members. Last but not least, I would like to draw your attention to another event that is related to the gender equality in science. This event is called the International Union of Pure and Applied Chemistry Global Women's Breakfast. That is organized by Professor Katja Loos and probably many others. And the event will happen on the 16th of February at 9:30 a.m. In Gathertown. So we highly recommend to join this event as well, and we will put the corresponding link to the Gathertown in the Zoom chat here. All right, then this is everything I wanted to say for the introduction. So now let me stop sharing my screen. I would like to thank once again our speakers for accepting our invitation. And now I will give the word to Akshara and Stephanie, that will be the chair of the event today. And I wish everyone an interesting and fruitful event. So Akshara, please go ahead.
Great, that was on time. So good afternoon, everybody. So we will have 2 scientific talks before we take a break. The talks are 20 minutes with including time for questions. So I will also give a 5-minute and 2-minute warning to the speakers, so the life is easier for all of us. Okay, so first online we have Professor Irene D'Amico. She is a full professor at the Department of Physics at the University of York. She's leading the Semiconductor Spintronics and Quantum Information Research Group. She's also one of the pioneers in proposing all optical semiconductor-based quantum computation devices. And more importantly, she's been the chair of Department of Equality Committee from the creation of the committee in 2009 until 2013. Today, she will introduce us to quantum information processing with a particular focus on noisy intermediate scale quantum devices. So the virtual floor is yours, Irene.
Thank you very much for this very nice introduction. I will share my screen. So hopefully you are now seeing the presentation. So first of all, let me thank you for the organizer for this very nice invitation. It's really a pleasure to celebrate with you the International Day of Women and Girls in Science for this year. I'm from the University of York, and as our chair has mentioned, I've been working toward equality, gender equality in science for a few years now. So again, it's really a pleasure for me to be here today. Today I will be talking about distributed quantum information processing with spin networks. It's a big mouthful, so I will go through an introduction explaining all the various terms. I understand that the audience is quite varied. But first of all, let me introduce my collaborator for this particular work. We have Luke Mortimer, who is now in Spain at the ICFO, Dr. Marta Estarellas from Kilimanjaro Quantum Tech and the National Institute of Informatics of Japan, and Professor Tim Spiller from the University of York. One of the reasons why I chose this work to be presented is that this is a work stemming from the final year undergraduate project of Luke. So I hope this will inspire young minds to, produce really interesting science at the forefront of their field, as Luke did. So, as I said, I will briefly introduce quantum information processing and device, what we mean by quantum wires, and a bit the protagonist of my talk, my work, that are spin chains and spin networks. I will give some details about our own work, talking about our new evolutionary algorithm for doing quantum processing with quantum information processing with spin network, and some examples of applications. So quantum information processing, what probably is most known about it is quantum computation. And what I'd like to underline really in a nutshell is that it's not the traditional computers, the one with which we work every day, are not really based on quantum mechanics, in the sense that to build up their hardware, their microchips to read, for example, some of the information via lasers and so on and so forth, you actually need to know quite good amount of quantum mechanics. So there is quantum mechanics also in our traditional computers. However, a difference with our traditional computer, quantum information processing and quantum computation, are explicitly based on the laws of quantum mechanics. So also the theoretical part, the way we make gates between different units, are based on really the core of quantum mechanics. And at the core of quantum mechanics, there is an important principle. This is the superposition principle. Your system can be in different states at the same time. This is in a nutshell, the superposition principle. And this provides a very powerful parallelism. You may be familiar with parallelism in traditional computation. You know, it can speed up all sorts of algorithms. Quantum mechanics gives this, well, a similar parallelism to you for free. And so if we are really clever, we can exploit it in order to do computation or information processing in a much efficient way, in a more efficient way than traditional information processing. To make really the basic example, in traditional information processing, we have as elementary unit the bit, and the bit can be in either 0 or 1, but not in both at the same time. The quantum bit, the qubit, can instead be in, let me call it quantum 0. I put this 0 in this funny bracket, so let me call it quantum 0 or quantum 1 at the same time. So in general, it will be in a superposition of the two. This means that if we have two qubits, we can have that the same state, just a single state, can be in a superposition of 4 different states. If you have n qubits, n qubits, this can be at the same time in a superposition of 2 to the n states. And to give you just a reference, numerical reference, if you have 20 qubits, then this can be in a superposition at the same time of more than 1 million states. So you can basically represent at the same time and work at the same time with more than 1 million numbers of 20 bits each, 20 bits long. If you only have n bits at the same time, so simultaneously, you can only write down a single number of a length of 20 bits. This gives you an idea of the type of power that, if it is properly used, can be unleashed when you do quantum information processing. So until relatively recently, lots of people were thinking of quantum computation as something very much into the future or in the realm of sci-fi. Actually is already hitting the market. The first company that started commercializing let's say analog quantum computers that cannot perform universal quantum computation but specific tasks, was D-Wave, and it started in the 2000s. Much more recently, both Google and IBM have joined the market, forming specific new division in both, announcing them in 2017. And very recently, November 2021, IBM have constructed IBM Eagle. This is a quantum computer with a quantum processor with 127 qubits. Indeed, this is a very, very nice achievement, which leads me to talk about NISQ devices. So this is where what we are living now, is indeed the age of NISQ devices, quantum devices. So what does it mean, NISQ? NISQ means noisy intermediate scale quantum devices. Intermediate scales means that we are dealing with something of the order of 50 to a few hundred qubits at the most. So this is the size. Noisy means that these are not still really optimized devices. They will be very sensitive to the environment. So they will have only moderate accuracy. They will be prone to errors, if you like. Also because of the low number of qubits, we cannot really implement a proper quantum error correction algorithm in them. And in this respect, you may be able to show some quantum supremacy, but maybe not in a sustained way for all this reason. However, these are now relatively big, so relatively large with respect to the past quantum devices. And so you can really dream of doing non-trivial tasks with them. One of the question marks is to actually invent the tasks that can be understood, which tasks can be done with these devices. Also, it's interesting to develop algorithms that can already exploit the type of the amount of computability in these devices, and some of these have already been proposed. And similarly, we start to have problems in actually, once we have these ideas about this algorithm, how to implement them in the most efficient way in the device we can build in the lab. For example, how can we tune in the most efficient way the parameters in our devices in order to really be able to perform using these limited devices the type of computation or function, quantum information function that we want to do. And this is a bit the subject of my research, the research I will be presenting today. So, for example, we can already imagine that even in these devices, we will have the necessity of connecting some different processor through what we can call quantum wires. And we need this quantum wire to at least transmit coherently quantum information. So not just information, but quantum information, maintaining the quantum point in it. But we would like this quantum wire to do more, actually, to be able also to perform some specific quantum information processing. So, for example, being able to do quantum gates between different processors or produce entanglement is very important. And in this respect, spin networks or spin chains have been demonstrated, at least theoretically, to be very good. And a spin chain or network is what the theme says. So it's a chain or a network of sites. In each site, I have a spin that can be either up, which will be my quantum 1, or down, my quantum 0. And on which one side I will have it's only one spin. They can be implemented with various hardware, from read atom to quantum dots to molecules and so on. One thing that is interesting with this hardware is that we can think of doing all this functionality by simply waiting. So I prepare a state, for example, in a chain in spin 1, I just wait, and then I obtain the same state in spin n. So we have been thinking of using this type of devices in the context of NISQ devices in order to describe NISQ devices with this type of model in order to be able of produce different functionalities. And the problem at hand here is I have a specific quantum network. I have a specific quantum task I want to do. How should I tune the parameter in my network in order to be able, with that particular network, to achieve that particular task? And this is the problem that we have gone into solve and proposing a solution. And what we have done is to devise an evolutionary algorithm for doing exactly this, so tune our parameter. So we start our algorithm with a certain network and a certain task as an input. We do genetics, the computational genetic type. So we have parents and we create the parents network. And from there we can create a better child network with more efficient child networks. And when we are happy with it, we say, okay, this child network, so this network with this specific parameter is the solution to your problem. The algorithm is very efficient. It's based, as all genetic algorithm, on a specific fitness function that we have created, which favors high accuracy and short time to perform the task. And let me do some example. For example, we take one of the example is to take a shoelace, so this type of network, and asking the network if I give a specific state in the site A, can I get it out? Just waiting a bit of time in the site G, And indeed, by adjusting correctly the parameter, by tuning the parameter, we demonstrated that you can do this with almost 100% fidelity in a relatively short time. But you can actually use the same network, the same shoelace network we have demonstrated, not just for this simple information transfer, but even to create entanglement. So again, I input just one of the sites. We just chose one of the sites, let's say site C. And I wait some time. I don't do anything else. I just wait. And I can add as output an entangled state. Entanglement is extremely important in quantum computation between A and G. Also, we have demonstrated that we are able to adapt we choose a square lattice because this is a good, a kind of common type of connectivity, and we can adapt this lattice to perform an entangling two-qubit gate. It is important because this allows for universal quantum computation. So this is the idea. Our input in 2 qubits, we wait some time and we get the output we want, so an entangled state in the output. And again, we have been able to produce this very efficiently with our algorithm and with extremely high accuracy, almost 100% accuracy. And what is important for experimentalists is that actually we can get this high accuracy even when we think of relatively big imperfections in our system after when we try to tune our parameters. And this is a quite large type of optimization because there are 28 parameters to be optimized. So it's a really nice story. The algorithm is easily parallelizable and scales well and compares very well to other possible algorithms, which brings me to the summary. So I have been telling you in a nutshell what is quantum information processing and where we are now with quantum computers and the like. I've been telling you that we are in the era of NISQ devices, these noise intermediate scale quantum devices. And I have briefly introduced our own research on producing a genetic algorithm able to answer the question, I have a certain quantum network, I want it to do a certain task, how do I do? How should I tune in the lab the parameter of my network? So thank you very much for your attention.
Thank you so much, Irene, for the amazing talk. I'm sure we learned a lot about quantum computing. So I'm sure there are a lot of questions. So if people can raise their hands, I can allow them to speak. Okay. Jan?
Maybe while other people are thinking of good questions, I wanted to ask, are there already quantum computing systems that can work on, let's say, everyday temperatures? Or do you still need very low temperature system to get this working?
Sorry, I've done something silly here. Sorry, I did something silly on the on trying to share something. No, the quantum computing devices, which I introduced before, work at extremely low temperature. So both, well, all of them really, the Wave, IBM, and Google, all of them are based on superconducting qubits. And so you have to go to really low temperature for them.
Okay, thank you very much.
You're welcome.
Great. We have Alba, who has raised their hand.
Yes. Hi, do you hear me?
Yes.
Hi, thank you for the interesting talk. So very, very basic question. You mentioned that you need to, let's say, preserve the quantum part of the information. Can you say a bit more about that? Because maybe you already said it, but I didn't really understand.
No, I didn't say much because clearly, yes, I mean, it's so when I let me try to go way back. When I let's do this. So if we look, you can see my screen like. So when I introduced the quantum superposition, okay, I said that the great thing is that you can write your state in this way. So it's a superposition of many states. However, this superposition is very fragile. So if you have unwanted interactions with the rest of the world, we can simply be something in your lab or a stray magnetic field and so on. And then what happens is that this superposition will be altered or even broken, and you can go back to a classic result. So instead of having a superposition, you just get one number. So this is what I mean, is preserving this type of superposition that is the difficult thing. Yeah, the way you want. Yeah. Thank you for your question.
Great. So last call for one more question, if people have any. Okay, so I'm going to take the privileges of being the chair and ask a question. So you did in the controlled phase space, that slide, if you can show me.
Sure.
No, I just wanted to show the question in the slide.
Oh, sorry, do you want to share your screen then? Okay, let me stop sharing.
No. It was in your slides.
Okay, so let me go back to share. Okay, you want to go to the control.
So the one with the tables, I guess.
This one. Yes.
Yes. So it says that you've tried to optimize 28 parameters. So is there like an upper limit for the parameters that you can send in through the control?
Well, the more parameter, of course, the longer the time. So we have looked at scaling in this respect. And we have looked at scaling with a different type of device of a linear chain because the point is you also have to have a clear target when you look at scaling. So you have to know that your system will be able to do that particular task. And we know that it's possible to have a perfect transfer of information across linear chain, and we know the solution. So we have checked how our code can reach this solution for increasing number of parameters. And so the scaling is exponential. It's not what you would like in principle, but the exponent is very, very small. So to give you an idea, we can go up to, this is the number of parameters, if you like. We can go up to 33 parameters, from 12 to 33 parameters for this problem in just 40 seconds, and 40 seconds with 4 cores, because the system is basically linearly parallelizable. So if you have 8 cores, you would go down to 20 seconds. If you have 16 cores, you would go down to 10 seconds and so on. So the scaling is very good. It's barely exponential, if you like. So you can really go up to a much larger number of parameters and still be able to do this type of optimizations. Yeah. So it's very good news from this point of view. Yeah.
Great. Thank you. Thank you so much. So thank you so much, Irina, for the amazing talk, and thank you to all the people who had questions and asked them. Feel free to ask some questions in the break if you have any. So moving on, we have our second speaker before the break. So we have Professor Ivone Albuquerque. She is a professor at the Institute of Physics in USB, and she's closely working on the physics of elementary particles and fields, mainly on dark matters, neutrinos, cosmic rays of very high energies, particles, and extensions of the standard model. So today in her talk, we will learn more about dark side experiment and its contribution in the search of dark matter. Over to you.
Yeah, thank you very much. Let me share my screen. Let me see if I can put, yeah, are you all, can you see the screen? And okay, thank you. So, so thank you for the introduction. So we are here in São Paulo, Brazil. We have this astroparticle group, which consists of myself and Professor Edivaldo Moura, and with many students. So I think I congratulate you for the celebration of this day. I think it's very important. I think all around the world, including here in São Paulo, we are trying to find ways to guarantee that there's more gender equality, and I think that's a very important effort. So thank you for the invitation. So as part of our project, we have, as was said, I am part of a collaboration that's called DarkSide that looks for dark matter in the universe. So I will give an introduction of why the observations and evidence for dark matter and the efforts to try to understand its composition. So let me see, seems I can't, let me, oh, here. So normally, so dark matter is a component of our universe. And normally, when people think about having information of the universe, what we think is the light that comes to us from astrophysical objects. So we have our telescopes, and what we measure usually is the light that comes from both galactic or extragalactic or objects like quasars that comes from very, very distant from us. And what we measure is the light that arrives to us. So in all frequencies of light, we can measure light coming from these objects and try to understand the processes that happens within these objects. So we have here a wide spectrum of wavelengths or frequency that the light comes to us. And we know that the known matter, the matter that we know, like protons, electrons, and all the particles that consist the matter that we know, they interact with light. So we say that they interact electromagnetically. And so we can infer a lot of processes within these objects and relate them to the particles that interact with light. So this is one way of understanding these objects. And one of the key things is that we relate the luminosity that reaches us with the mass of the galaxy. So we can say, we know these, the way that these particles interact with light. We can infer from the luminosity we get what's the matter, the matter that's within this galaxy. So we can infer the galaxy mass through the luminosity. However, there is another way to infer the mass of the galaxy, and it's by the way it rotates. So we can infer how much mass the galaxy has when we measure the rotation, the way it rotates. So these two forms of estimating the mass of the galaxy were examined by a physicist, the astrophysicist Zwicky in 1933 or the 1930s, when he examined the coma cluster movement. So he examined this movement by these two ways that I just mentioned. So he made a mass measurement of this coma cluster is a cluster of galaxies. So he inferred the mass of this cluster by the luminosity that got to us, and also from the way that this cluster rotates. And what he understood, what he saw, is that the galaxy, the rotation, was too fast to be bound by the mass that we inferred from the luminosity. So the way it rotates would imply that if the mass consisted only of the mass we inferred through the luminosity, these galaxies would be flying out of this cluster because there wasn't enough mass to hold them together in this cluster of galaxies. So what he concluded was that 80% of the matter within this cluster had to be dark. By dark, he meant that it did not interact with light. And that's where the name dark matter came from. So there was this contradiction. He saw that, if the mass that we infer from the luminosity was all we had, it wouldn't be possible to keep these clusters within this galaxy cluster. So this was one of the first ideas about dark matter. Zwicky was a very important astrophysicist, but people at the time didn't pay much attention to this conclusion. So it was only, decades later in the 70s that this astrophysicist, Vera Rubin, she started to analyze the rotation curves of galaxies. And one of her ideas was to check what Zwicky had concluded. And what she realized is that if you look at this graph here, if you get the contents that interact with lights in the galaxy with stars and gas, it has this behavior, which is what we would expect from Newton's gravitational law. However, the velocity of the galaxy did not follow only what is expected from matter that interacts with light. It did continue in a way that you have to have a very big component that's not the matter that interacts with light. So she got to the same conclusion as Zwicky. And as you can see, you need a dark matter, you need some kind of matter that doesn't interact with light in order to be able to understand how the galaxy rotates. So this was a confirmation of the necessity of having some matter that does not interact with light, which we call dark matter. And she measured many galaxies, and they were all consistent with having dark matter. So here's our two examples measured later on. And so the dark matter was observed. You needed some kind of matter that didn't interact with light. So later on, you had many other independent measurements. And I'm going to give here the examples, these examples. So another evidence of dark matter is based on what Einstein predicted. So Einstein, many decades before it was measured experimentally or observed, he predicted that light, when light is traveling through the universe, if you have a mass that's nearby it, it will make the trajectory of the light bend. And that's called, this effect here can be seen in this, it's called lensing effect. And you can see these arches here in light is due to the presence of matter. So if you have a background galaxy that emits light and will get to us, you will see that if you have a mass like a cluster of galaxy in between the light that is coming and the observer, it will bend depending on the mass of this intermediate cluster of galaxies here. And by the arc that you see this, this lensing effect, you can estimate the mass of this intermediate cluster of galaxies here, the galaxies in the main. So you can see the arches and infer the mass. So it's an independent measurement from what I mentioned before, the rotational velocity. And when you do this measure, you infer that the dark matter component within this intermediate cluster of galaxies needs to be with the same fraction as what you inferred from the galaxy or cluster of galaxy rotation. So it's a completely independent, and you get to the same conclusion. The amount of light, the amount of matter inferred from the light that comes from this galaxy is not enough to explain these arches here, the way that the light bends. So you need more matter. You need matter that does not interact with light and in the same amount that you observed before. So another way also to infer is the gas that's contained within a cluster. So this is the coma cluster again, and this is the hot gas that is contained within the cluster. So you can see this both in X-rays. So this is a measurement through light. And you can also measure it either in the visible, that was done by the Sloan Sky Digital Survey, and also in infrared. And when you compute how much gas you have within this cluster, what contains the gas is again the mass that's present in those galaxies. So once again, in order to be able to contain this hot gas, you need more mass than what is inferred by the light. So once again, you need mass that does not interact with light. You need a huge component of dark matter. A different way is to understand the fluctuations of our primordial universe and the way that it developed to become structured, to become, our galaxies and everything. And this, once again, is only possible. What we get from this temperature fluctuations in the early universe is compatible with having dark matter. It could not be explained if you had only the known matter that we know. And one of the more direct evidence of dark matter is what we call, we call the interaction of two cluster of galaxies. So this is animation from the first of these events that we measured, that's called the bullet cluster. When you have two clusters of galaxies interacting, maybe colliding with each other. So what happens is that in this collision, you will have the known mass that interacts with light, interacts electromagnetically. When it interacts, it is slowed down, and it will be mainly in the middle here. While the dark matter, as it does not have this kind of interaction, it will just go through as if it didn't collide. So when you analyze these kind of events, and today we have a handful of them, you see that in this region here, blue, is the dark matter that passed with no collisions. And here in the middle, you have the concentration of the matter that is known that did interact with light. So you can make an analysis of the mass distribution, and you will see that the concentration of mass is where dark matter is. So it shows you that this collision, the dark matter just went through without interacting electromagnetically, and the concentration of most of the mass after the collision is far away from the center. And this is expected from when you have a large fraction of dark matter in your cluster of galaxies. So as we've seen, we have independent measurements that, all these events aren't related among themselves. And we see that they all require the same amount of dark matter. So if you get just the matter of the universe, this will be close to 85% of the matter being dark matter. So, but when you analyze the whole composition of what's the distribution of that we have within the universe, we'll see that 30% is about 30% or 25% consists of matter of the universe. Within the mass, we have that dark matter is the huge fraction of this 25% of matter. And the rest is something even more unknown that we call dark energy. And that's a completely different talk. It's also comes from observations, maybe of the way that supernova acceleration, but this is completely unknown. Dark matter, we at least know that it is matter. But so what we're doing here in our group is contributing to the effort to try to understand what dark matter is. So we know that it's none of the particles that we know. And we're trying to decipher what is it constituted of. So far, we already shown that the known particles that we know, the standard model of elementary particles, which are the particles like protons, neutrons, electrons, and their constituents, or the quarks and neutrinos, we know that these particles are not dark matter. So we're trying to find what is the composition of this unknown matter. So at the same time that, we have this cosmological evidence for dark matter, on the Earth, at CERN, at LHC, which is close to you guys, scientists are looking for new particles. And we know experimentally and theoretically that the standard model of elementary particles, when you go to higher energies, they will need to be expanded. We'll need to find a model that expands the standard model, and within this, there are predicted new particles. So in the CERN, so these new models that they are looking for, they have candidates for dark matter. So this is very nice because you join two fields. While cosmology observes the dark matter effects, or in other words, you know that these effects are there, particle physics offer dark matter candidates when they propose extensions of the standard model. So with this, we're looking now to try to detect and pin down what is the dark matter composition. So there are mainly three ways to look for dark matter. So one is, at colliders like in the LHC, where you collide known particles and expect to produce dark matter particles from this collision. You have direct detection when your dark matter interacts with a detector. And then from the scattering of these particles, you can pin down the composition. And you have indirect detection when you have two dark matter particles interacting with each other, let's say in an astrophysical object like the sun, and then in this interaction, they produce known particles. And what we're gonna measure are the known particles. Our efforts here in USP has been, we joined a collaboration that tried to direct detect particles. And we also analyze particles from indirect detection. So I'll go briefly through these two. So the direct detection.
Sorry, Ivone, for interrupting. I think our minutes is up, so it'll be nice to have the summary.
Oh, okay. So direct detection, mainly you expect your dark matter particle from your, the halo that has in our galaxy to interact with a detector. In our case, we have liquid argon, and scatter. So you can measure directly the interaction of the dark matter with our detector. So this rate depends on astrophysics and particle physics. So you have the density of dark matter, you have the way that the cross-section, the probability that your particle will interact in your detector, and so on. So there's many experiments around the world doing this. We participate in this one where the detector is in Italy called DarkSide. I won't have time to go through it, but it's an international collaboration. So I will skip the details of the experiment, but the main idea is, as I said, the dark matter will interact with the organ that's within our detector and send light. This light from this interaction the light comes from the nucleus of organ, will be what is measured. So there's many details about this, but I will go now to what we're doing in USP, which is normally you look for dark matter at a scale of energy that's considered high. That's like 10 GeV over C squared. So one of the questions is, up to now, no dark matter was found. So we scanned a region of, this would be here on the y-axis, the probability of interacting in your detector versus the mass. So since we did not find anything yet on the region where we expected to find a particle of dark matter, both experimentalists and theoreticians are looking for ways to go to lower mass. And in our institute, we showed that you can do this with the DarkSide detector. And we have even though our detector is very small compared to others because it was testing the organ as the target, we showed that you can go to low masses. So this was done in our institute, and we have the best limit at small masses at the time. So just to finalize, I'm gonna mention the indirect detection. And the idea here is that dark matter particles will be falling within astrophysical objects like the sun. If they interact with one of the nucleus of the sun, their velocity might go lower than the escape velocity of the sun. This will make it captured by the sun. And when you have many dark matter particles in the sun, they can interact among themselves, annihilate, and produce neutrinos. So then we have a detector that can, at Earth, what's called IceCube, another detector is called Antares, which can detect these neutrinos. And this would be the indirect way of detecting dark matter. So finally, I can say, welcome to the dark side.
Thank you, Ivonne. That is a very amazing slide to stop with, I guess. I'm sure we have so many questions for this amazing talk. So can I see rise of hands for people who have questions? Julia, you can unmute yourself.
Hello, not sure if
Hello.
You can hear me. Yeah.
Yes, I can.
Okay, thank you. Thank you very much for your talk. So I was a little bit confused about the part where you said that the dark matter interacts with argon, because at the end you said that what we detect on Earth is actually the neutrinos produced by the annihilation, right?
Yes.
So I wasn't really sure like what we are actually detecting on Earth, if like the dark matter itself or the neutrinos.
Very, very good question. So in direct detections, like you have two kinds of noble liquid detectors, like with argon and xenon, and both of them are complementary. But the idea is that the dark matter interacts with the organ, directly or with the organ. So that's why, so we are detecting directly the dark matter particle going through the detector. So it will hit an organ nucleus, the dark matter at these energies will hit the nucleus of the organ, and the organ will ionize and emit light. So the light comes from the organ here. So it is directly the dark matter interacting in the detector. Was that your question?
Yeah, this is clear. And if I can ask just one more thing
Yeah,
from
sure.
what you said. So like, how come we expect dark matter to interact with like the matter we know? Like, how do we know this interaction is going to happen?
Yeah, so that's a point that's very good because people get confused. So what emits light here is the organ nucleus, not the dark matter. So the dark matter will, in this interaction, there will be energy transferred. So you will have some energy going to the organ due to the dark matter. And the organ itself will scintillate light because it will go to a higher state here and scintillate some light. So who's interacting with light here is the organ, not the dark matter. Oops. So with this, we have two signs. So when the darkness, so this sky here represents the dark matter and this the organ. So there's energy transfer and the organ ionize and scintillate some light that is detected. And also you have electric field here and you have the electrons and the ionization due to the electric field will go up. Don't know why it is. And there will have a second signal here on the top. So what's emitting light here is the organ, not the dark matter. Hope it was clear. But it's a very good question. Thank you.
Thanks.
So we have Martha who's raised her hands.
Yes, first of all, thank you for the very nice talk. I have a questions for you on YouTube, so I will read it for. So Alex wrote, "Hi Ivonne, thank you for an interesting presentation. The bullet cluster observation are very direct evidence for dark matter. Are there theories for these observations that don't require dark matter?"
So the bullet cluster is one of the, there's another kind of explanation for like the cluster of galaxy or galaxy rotation that's called modified Newton dynamics. So based on these observations, some people have a theory that what has to be changed is the Newtonian dynamics of clusters. And it's based on the way, the velocity of galaxies. However, MOND is called modified Newtonian dynamics, have problems when it tries to explain other evidence of dark matter, and the bullet cluster is one of them. MOND cannot explain the bullet cluster because it's, as I said, it's just the interaction really that goes on. It has nothing to do with the rotation of the galaxies. So far, the bullet cluster cannot be explained by other theories. And that's why it's one of the strongest evidence of dark matter.
Thank you.
Okay, thank you so much, Irene and Ivonne, for your amazing presentations. So we're way into eating up our break time, but I still propose we take a 5-minute short break so we can meet at 14:05. But feel free to stay on the dark side and ask more questions to Irene and Ivonne if you have any. Yeah.
I would suggest that we test Francesca's presentation if everything worked. So we can start right afterward.
Sure. I will share my screen, or?
Yes, please.
Yes, please.
I mean, we just did it this morning, but
yes,
to be sure.
Let's try. Exactly. Can you see it?
Yes, looks good.
Okay.
Francesca, one other question. If I
Yes.
do this, can you see it?
If you do this,
On
what?
my
Yes, I can see it actually, but just a second, because if I go in full screen mode, yes, try to do it again.
yes.
Yeah, I see it.
Okay.
So that I guess it is a -5, right?
Yeah. So I
end.
was thinking doing a -5 and a -2. If
that's okay. I will just ignore them. Yes. No, just kidding.
Okay, great. Then
Yes.
I think we're all set.
Stop sharing.
Maybe while we are still in the break, Ivonne, can I ask you an additional question?
Yes, sure.
I was wondering, what is the main reason that the dark side experiment is sensitive to way lower masses compared, for example, to the Xenon 1T experiment?
Let me put that's because what we call a form factor. So one of the advantages of Xeno is that it has a high atomic number. So, you have more nucleus, more protons and neutrons than in argon. So the cross-section for Xeno is higher. However, the way that the interaction between a dark matter within the nucleus happens depends on the distribution of these nucleus, the neutrons and protons. As you have less for argon, the form factor for the argon facilitates at lower energy than for higher energy. So it's mainly the distribution of the neutrons and protons within the nucleus, or the way we assume this, what we call the form factor is. So I don't know if I don't have my screen here anymore, but I have a slide with the difference from argon to xenon. But the plus side of the argon is that we have a kind of signature that's in the time of the signal that makes us be able to get rid of a background that's in a very strong way that's not allowed to xenon. So xenon has the advantage of having a high atomic number, while argon has this, what we call post-shape discrimination, which allows you to separate the electron interactions, the nuclear interactions with the electron interactions. So I would say, you know, it's complementary, and having both kind of experiments is very, very important. There's a question here. I'm only seeing it now. I have a question that seems to be so much as a great product, but a few decades certain and we haven't seen it. And the solution, oh, okay. So this is, so did I answer your question? And then I'll go to this question in the chat.
Yes, it was crystal clear. Thanks.
Okay, thank you. So yes, so this is a question that many...
do think we need to move to the next session a bit.
Okay.
So I think if you quickly, if you can give a short answer.
Okay, a short answer is that it might be that dark matter only interacts gravitationally. That's all the evidence we have it through the gravitational interaction. The detectors we have assume that it also interacts weakly. So first of all, we still have a lot of space to look for dark matter with a weak interaction, although what was thought as the most important region was covered. Second of all, it might be that dark matter only interacts gravitationally, and then right now we don't have the technology to measure the candidate, the composition, if it only interacts gravitationally. That's the short.
Thank you.
So I
much.
am sorry I have to leave when I wasn't, I apologize for that, but have a great discussion.
Thank you very much for joining us and your excellent presentation. Okay, so wait, the screen went to full screen. Yes, so we're ending the break here and going to the second half of the event. So what we saw in the first half was we had two very interesting presentations about the work that two very prominent female scientists performed. What we're now going to do is we're going to focus a bit more on gender and other diversity issues in the second half. So we will have two talks about women and minorities in science, one by Dr. Francesca Primas, who is going to present next. She's an astronomer at the European Southern Observatory. And then afterwards, Dr. Tana Joseph will give a talk. She's currently an astronomer at the University of Amsterdam. And both talks will again be 15 minutes with 5 minutes for questions. So let me just introduce our first speaker. This is Dr. Francesca Primas. As I said, she's a full astronomer at the European Southern Observatory. Her main research interest is the chemical evolution of galaxies. But for nearly 20 years, she has also been involved in several initiatives and working groups that promote gender equality and diversity, such as the International Astronomical Union Working Group on Women in Astronomy. And in this talk, she will tell us about recent initiatives that are in place to promote a more diverse workforce in the astronomical community. And the talk is titled How Astronomy is Pushing Equality, Diversity, and Inclusion Forward. And she will discuss the expected effectiveness and the progress made by these efforts. So I would say, Francesca, please take it away.
Yes, thank you so much, Stephanie, and all the organizer and the audience. I mean, and it's a pleasure to be here and talk about this. So I think that it was tough, actually. So when you invited me, I thought, oh yes, I mean, I have all the material. I mean, I've been involved in many of these initiatives. But then you try to put things a little bit into a context, and then you stumbled upon words like you mentioned, effectiveness of the measures, and that is probably the most difficult thing to measure at the end, to be sure actually, and to understand, to try to identify which initiative work better than others, and so on. So I try to, it will be a bit of a mix. I try to give you, instead of just a kind of list of all the initiatives, I selected a few. Feel free to ask for more, but I think that I want to give two aspects. An aspect which is really to raise the awareness within the community about these topics. And another one is a more pragmatic approach in trying really to change and have some impact. and possibly on very short time scales. So let me just start. So just to set the stage and the context, EDI matters because, because I mean, now we have quite some proof and some literature about it, that diversity, especially in teams, in research teams, actually increases productivity and creativity. We may not be so caring about the economic growth, even if, of course, it does touch upon us and where we find our funding, obviously, but I think that overall, it just gives the chance to listen and to hear and to share different perspectives. And I think that this is extremely positive. So as I always say, diversity is the mix that we want really to achieve, and inclusion is what makes this mix work. And it seems a silly statement. I would like to consider it a silly statement in a sense that it is common sense. Why should it not be inclusive, and why should we be discriminating? And however, I mean, we do that all the time, and we are biased, and we are discriminating. We are not so much diverse, you know. When it comes to diversity, I think that when we talk about hiring, for instance, you know, hiring a person who is almost your clone, you feel immediately on the same wavelength, you connect, you know, with this person, you will understand, and you will have a very good understanding with this person from day number one. But instead, you should really always get out of your comfort zone and try to hire somebody probably who is the farthest away from you in order to bring in a completely different perspective. So when I talk about diversity and inclusion, diversity can have different aspects. One of the most common one and most studied one is gender. And also there, I think that we are scoring rather poorly in a sense that we are still very much stuck on a kind of binary gender. So at least all the gender disaggregated statistics, as we like to call them, I mean, they really look at females versus male. Okay, it is a step forward. It is, we do need to collect those data. But I hope that the community now is broadening up, I think, and it will take some years still to collect more data, a broader range of gender diversity. But you see, you can talk about diversity under many different aspects. Age is another one. So if you look at your own organization, university, department, you can make just some age beans and see how you're doing. Inclusion is really to value, is really to work on your working environment, I would say, to make it a more inclusive and more enabling environment for everybody. So just to look at where we stand for astronomy, I think that in the USA, this longitudinal study that was published a few years back already, but basically is looking at 30 years of data. And you see that in terms of bringing in students into the astronomical field, into the astronomical studies and faculties, I think that it does not look that bad. We are not at gender parity, as it is true, for instance, in Europe. Overall, across all disciplines, I mean, we have reached gender parity. Again, gender is male versus female, so please allow me to use gender in that context. In astronomy, we are not there yet, but I think that the numbers have improved, as you can see, right? So, and this is confirmed by, this is just an age bean of the IAU members. So we are talking about 12,000, 13,000 members right now that are member of International Astronomical Union. You see that actually the beans, the youngest bean, I mean, we are already approaching the 50% among the members. There are a lot of caveats, and I will not enter in all the caveats of these numbers of the IAU, because just simply not all astronomers on the planet are members of the International Astronomical Union. The Gender Gap Science in Science project was a cross-disciplinary project that IAU engaged into, and that I followed rather closely. And I think that I just want to bring here the outcome that even if these numbers look good, and we are moving forward and we are improving under certain aspects, I mean, the situation, I think that what has come out of this project and of a joint global survey for scientists is that the gender gap in science is real. Across disciplines, across regions, geographical regions, continental regions, and across all human development index levels, so the HDI, from the United Nations and so on. So it looks that is a real problem and is there. And as a matter of fact, women have in fact expressed more discrimination, more harassment, more interruptions, lower pay, slower progression. I mean, you can put whatever you wish there on that list, and it will probably even grow and further grow. You see the numbers, the difference when women felt more discriminating than men. I mean, they are impressive number, and we cannot just ignore them. So astronomy, I think, that has paved the way in this field quite early on, and I'm very proud of, of being an astronomer overall, but also of belonging to a research field where there have been so many actions. So I think that we have 3 very important historical documents, and the first one actually dated back this year is the 30th anniversary of a very famous Baltimore Charter. And then we had the Pasadena recommendation, we had the resolution approved at the International Astronomical Union. They all focused on equality, diversity, career paths. So, I mean, the focus was already there in 2003, where it was already identified that career paths, hiring, retention, promotions are very important aspects. And we are not doing a very good job in order to retain women, for instance, or a more diverse workforce. I think that diversity per se, in its broadest meaning, has come in a little bit later, let's say, in this area of in these discussion forums. We have organized the very first inclusive astronomy conferences. These are mostly in the US, both of them in 2015, 2019. This one brought in, as I said, I mean, inclusion and diversity came a little bit later, as it is demonstrated by these conferences, and they looked more actually how to make it more accessible, how to deal with why are we discriminating always against colleagues with different degrees of disability, for instance. And in fact, I mean, ESA, IAU, ESO, as well, SKO, join efforts, and we organized a meeting a little bit more than a year ago, which was called the Space Science and Astronomy Research Accessibility, really to look at, in even very technical aspects, how to make something more accessible. It could be just a data archive, for instance, right? Is a blind person able actually to look for data in the science archive, or to do something? Because we do have blind astronomers working, professional astronomers who actually have an active research career. IAU is extremely engaged, and I think this is the institutional or even professional union type of approach. It has a strategic plan, which include inclusiveness. I mean, we have working groups, as Stephanie mentioned already. There is a Women in Astronomy. Now we have a very strong equity and inclusion working group. There is a gender gap project, which I just mentioned. I think that a very positive aspect or point and achievement that I consider as such was the fact that the Astronomical Union actually approved a full symposium. I mean, the IAU organizes usually between 5 or 6 symposia per year, except for the year where we have a general assembly, when there are more. But dedicating one full symposium just to the theme of astronomy for equity, diversity, and inclusion, I think that it was a very bold move, and it was very well received, and it was an extremely interesting meeting, from which we have now a springboard to action document that I encourage you all to read. These are very high level recommendation and guidelines, but I think that this goes in the direction of actually raising the awareness, what people can do. The IAU cannot tell a member country, do this, do that, but they can, let's say, behave by example. So that, I mean, we have it has a psychological cascade effect also then to the member countries to do something and to act. Now, yes, and now I will move it to the second aspect, as I said, a much more pragmatic approach. So what is an astronomical career research in research, right? So basically, both observational and theoretical observers, I mean, at a certain point, they will have to deal with data, or to analyze the data and find some results, or to use the data in order to create theoretical models. Therefore, I think that is really at the heart, at the core of our research career. So winning and telescope time. And telescope time is a very competitive process, because, I mean, there are a lot of people applying. For instance, our facility at ESO, I mean, they are open to the entire world, so there is not much of a difference, like HST, like many other And therefore, it's quite tough actually to get time, and you need time. I mean, if you're an observer, if you're a student, if you're a PhD and you're working on your thesis, you need to secure a set of data in order then to have actually results to present and to build upon your next steps, your next career steps. So what was found back in 2014 was at the telescope, they analyzed some of the data, and they looked at that over a period of 10 years, the success rates of female PIs, of principal investigators, were lower than their male colleagues, their male PIs. And on top, there was an age effect, meaning that the younger PIs were actually performing better in terms of success rate than the older ones. And this exercise brought them very clearly the message. They said, well, 10 years is a long enough time baseline. And therefore, I mean, this is really a systematic effect. And this points towards implicit bias present in our review process. And ESO did the same a few years later. We looked at 8 years instead of 10, but we had quite a few numbers of proposals to look, quite a few numbers of reviewers. And you see that also here, this is basically shows the success rate across this period of 8 years for the top ranked proposals in the ESO system. And you see that the female PIs always scored less. They had less success than the male PIs. And the difference is quite significant. This was followed also by other big facilities like ALMA in the radio, NOEO again in the optical, ground-based facility, NRO again in the radio, and all found exactly very similar trends. Of course, there can be other biases like against nationality, against other let's say, other aspects, but this was really the main, let's say, the main result. And so what did we do about that? I mean, you know, in the moment that you come out with such results, you cannot really ignore it. So I think that the road was quite long, the path was quite long, I would say, because we went from try to gender balancing our review committees, training, giving them training on unconscious bias. Then we put all the investigators in alphabetical orders, moved them to the last page so that they could not be influenced too much to tackle unconscious bias. Then actually we took away completely the affiliation so that they cannot actually recognize, who the PI is. In the end, I think that what is started to prove actually to be working is really the double anonymous reviews that we have started to implement at the big facilities. And I think that the data, the first results, it's too early to say that this is really the solution, but I think that the data are very encouraging, showing that actually we are, the system, the review process, let's say, is significantly more equitable. And so I think that I will stop here. I have just a few closing remarks. The road is still very long, and who knows if we will ever reach the end of that road. I would like to say that without considering the issue of a telescope time request and the review process and the allocation of telescope time a solved issue, because we are working on it. And I think that the next steps, as we look forward, I think that we will need to tackle, here are just some ideas. I mean, we will start to need tackling the assessments aspects of our career. So what is not only career progression, is grants, but is also especially this very gender concept of what academic success means. And it would be good to have discussion and to have and to start changing actually a little bit how we consider that. This touches upon publication, and then we can work on visibility of people in conferences, in awards. I mean, there are a lot of things where we can increase, and it's needed, and there is room for improvement to increase in diversity and inclusion. Now, I mean, the EU actually has probably given us a huge help now, probably very much hated by a lot of organizations who did not have gender equality plans in place, but in order to push this structural change in the research organizations, actually, they are now asking to have a gender equality plans in order to access their funding. Now, the road could be significantly more like that, I think. than just a straight road. I mean, we are making 1 step or 3 steps forward, then 2 steps back, and then we continue to go. So we need to keep the focus. But my take-home message today is really that all actions count. And all actions, I mean, not only what I presented, that it can be more on the policy or something more pragmatic. I think that with all, I mean, all of us. I mean, you cannot always point the finger to your organization, university, that they are not doing enough. All of us actually can change by talking, by raising flags, by going to a conference, by looking around, keeping the EDI views, let's actually the EDI glasses on, and making comments, not being afraid to talk about, and if we see something that is very strange. And I will stop here. Thank you very much for your attention.
And thank you very much for the excellent and very interesting talk. I'm sure this is a lot of food for thought for everybody. So I would like to open the floor to questions. You can raise your hand if you have one. Yes, I see a question by Jan Gerald. You should be able to unmute yourself.
Yes, thank you. It's a very interesting talk. I'm working in the engineering part of Astronomy, and I'm actually tempted to say, and this is maybe a bit unfriendly or a bit challenging, that you're so extremely successful in astronomy, you don't have to do anything. You're compared to engineering, this is so much better, these numbers. If you look at engineering, if you look at the technical universities in the Netherlands, females 10%, 15%. If you look at the astronaut engineering departments, 1 out of 60. It's so. My real question is actually, do you think all the work that was put in this, in the plans that you mentioned in 1983 and etc., is that how much percentage is just societal change, or how much is real effort? But in other words, are the engineers too lazy and not putting any effort in, or is it more societal that you're so good in astronomy?
Honestly, I do not have the answer to your question. I think it is a very good question. I just joined this meeting from a different meeting where engineering was actually under the spotlight, because I think that we are all facing the same issue. So I believe that we do have a huge scarcity and lack of students already in engineering. And that is a major problem. So how can we change that compared to astronomy? And I think that astronomy is a very good selling research field, just because of this type of images, right? So that hit actually the brain of children, of adults, of people who may decide to enter at the university. So let's say young adults. And that is not an insignificant, let's say, role that astronomy has in society, also to share. I have a lot of colleagues working in physics and engineers. I mean, it's significantly, even from an imagery point of view, you know, it becomes immediately significantly more technical. If you think about astronomy, you don't think about the technical details of a telescope. Usually, when you go towards the public, you look at a star formation region, and that is fascinating, right? I mean, they all dream about, I mean, looking up in the sky at night, the stars and so on. So I feel that is one small part. Secondly, I do not know how much engineering, so I'm not really an expert on engineering, and I never really dig much deeper, I mean, into that research field. I know that astronomy has invested a lot of effort, to be honest, because I mean, if you think about its 30 years effort of having recognized that there was a major issues about female representation in the astronomical research field. And we are not there yet. So, I mean, that could be a depressing message to say, you know, better that you start early, and maybe your grandchildren or grandchildren will maybe see some benefit. I mean, this is how I work in my mind, right? I've seen improvements. But I think that the pace is extremely slow for these matters, because as I said, you make one step forward, then you make 2 steps backwards, and then you make 3 steps forwards, and then another one backwards. And yeah, I really do not know what to suggest. I think that engineering, for instance, from the previous meeting this morning, was indeed a field where a lot of efforts needs to be invested in high school already, to try to fascinate and attract students to take then engineering. And in engineering, even within engineering, there are certain branches that are almost completely devoid of diversity and women, right? I mean, they are extremely male dominated. And that becomes also bad. I mean, ESO is facing the same issue in a sense that we do have significantly lower fraction of female engineers. And honestly, we know that, you know, when you present ESO towards the outside and a possible interested female young engineer, I mean, looks at ESO, you know, and then they see how few women they are, they could just decide to say, no, that's not the environment where I want to go in. So you see, is a kind of, we are running in the same circle. So if we don't improve one, we will not improve also the public face that we give towards the outside in order to attract more women. So it's.
I think because we're already running over
sure.
time.
Sorry that it took too long.
No, that's fine. I would propose to round off this question session here, and then we can discuss more during the discussion afterwards.
Of course, yes.
Okay, so thank you again for a very interesting talk, and I look forward to the discussion as well, where we can dig into this a bit more. Then I would like to introduce our second speaker for the Women and Minorities in Science team. That is Dr. Tana Joseph. She's a South African astronomer, and she's very active in decolonization and diversity advocacy. She's a science communicator and an entrepreneur, and her astronomical research, she's also an astronomer, is focused on extragalactic X-ray binaries. But she has also done a lot of work in promoting diversity in the astronomical community. And because of this reason, she was appointed the coordinator of the Netherlands Astronomy Equity and Inclusion Committee earlier this month. So that's really great that we can welcome her here. And she will tell us about her journey from being a schoolgirl in Cape Town, who I think I read indeed looked at some of those beautiful pictures that were just mentioned in the question session, to now becoming a qualified astronomer who can work all over the world. So with that, I would like to invite Tana to share her screen.
Hello, everyone. Thank you for that nice introduction. Thank you for having me at your event today. I'm sorry that I missed the first half of this event due to having to speak at a Women and Girls Day in Science for an event in Nigeria. So it's a very global event, and I'm glad to be celebrating virtually with the whole world. So without further ado, I will share my screen and give you the same slides that I just gave, a very different audience, but I'm going to put a very different spin on it this time. So let's start slideshow. Right from start, here we go. So this is a talk I normally give school-age children, especially girls, how I became an astronomer. And I start with this beautiful image of a galaxy from Hubble Space Telescope, Andromeda Galaxy, our biggest, our closest big galaxy neighbor. And these are the kind of images that led me to become an astronomer, as I will unpack. So I want to kind of start at the very beginning of my journey into astronomy, just with this image. These were the some of the first and most beautiful images beamed back by Hubble in the mid-90s after they fixed it. And that really changed my life. So what I call my pre-astronomy years, just some photos of me in school, and what I will be doing as I talk about events that are happening in my life and the development of astronomy in South Africa and around the world. I also want to take time to highlight some EDI or social justice parallels that go along with this, and how we need to be very intersectional and intentional with our approach if we want to reach, full, accessible, and inclusive environments in whichever part of STEM that we're in. So my pre-astronomy years, in the picture on the left, I'm about 5 or 6 years old. This is actually a photo taken of me, and you can see I'm in the same uniform in the other picture where I'm about 8 years old at Welcome Primary School. And what's significant about this for my journey is that these photos were taken while I was still at a race-segregated school in South Africa, because I was born during the apartheid regime in South Africa. So they already coming from a time where I was born, where I didn't have officially recognized human rights. People who looked like me didn't have human rights. Apartheid has been designated a crime against humanity. That is my background that I'm coming out of. And so immediately you think, oh my God, this person is on the back foot and their story is so inspiring, and you think you're going to get inspo porn, but what you don't see here is a child who's already interested in science, because as it turns out, both of my parents are high school science teachers. My mother was a life science teacher for over 30 years. My father taught maths and physics at high school for over 10 years. Both of my parents are university educated homeowners, and they come from fairly middle-class backgrounds. So while we had this issue of apartheid, this massive issue of apartheid, when it ended, my parents were in the early 90s, around this time that these photos are being taken. My parents were very well placed to take up their middle-class lives, they're more typically middle-class lives, in a new democracy, and to pass all of those privileges and advantages on to their children. So when you look below the surface, there's actually a lot of privilege behind my journey. And so these photos here are me interested in science, but not yet specifically interested in astronomy. And then in the mid-90s, as I mentioned before, with Hubble, I started seeing these incredible Hubble legacy images. And here's a photo of me about 12 years old, about a year after I decided to become an astronomer. And the what and the why. People were like, we don't do that in South Africa, and that's not for our people, and you have to go work at NASA, and it's going to be, and my people were questioning my parents, but my parents had a lot of ambitions for their children, as most parents do, and they knew that with their support that I would be able to do this. They knew that I was capable, and I think that's something that when we do our EDI work, we need to really look at the data that shows us. Earlier on, there was that very pertinent question about, societal influence. And that is very important when it comes to especially racialized minorities. In South Africa, of course, I'm not a minority, I'm part of the vast majority. So when we use that language as well, I'm a minority. In the US, they use that word for Black people, or in the UK or whatever, but I'm African. I am the vast majority, and yet experience very, very similar racialized discrimination that you would call minorities in other countries. So when we make these plans, we need to think about your positioning in the world. Are the people you're trying to help actually minorities? If they're not, how does that change your strategy? All of these things we need to keep in our minds. So going back to the mid-90s, this was seen as something that was a bizarre choice, but my parents were determined. And we have evidence to suggest, for instance, in the UK, that shows that when it comes to getting girls interested in science and taking it up in the final years of high school and at university, parental support is actually one of the biggest factors. And I had that in spades. My parents are like dance moms. They're like pageant parents, show parents, like stage parents, but for science and for academics. So we need to keep that in mind. It's not just about engaging the young people themselves, but also their parents, their teachers, school principals, and the community as well. And that's something that's very different in different cultures. So as it turns out, it wasn't such a weird dream after all. With my parents' support, I excelled in my studies at school. You can see here my blazer. This is taken in the final year of high school. I'm 18 years old. I'm no longer wearing that retainer. The teeth are now straight. And I'm wearing a blazer with a gray trim on the edge, a gray binding to indicate that I'm a super nerd, because you get that at my school and other schools. You get that binding on your blazer when you get academic full colors. So it's like getting like I guess if you're at US institutions getting a Letterman jacket, but for being a nerd, for being very good at the exams and the tests and so on. And what's happening here, this busy image on the other side, is the groundbreaking for building the Southern African Large Telescope, or SALT, which is the optical telescope with the largest optical telescope emitter in the Southern Hemisphere. And this is in South Africa. So suddenly my dream is becoming more achievable now. And unbeknownst to me, I didn't know this was in the pipeline, but South African government had decided to invest in astronomy and use the fact that we have this geographical advantage of dark skies and lots of open land, and build some telescopes there. And we have some of the darkest skies in the world. So we're incredibly lucky, incredibly fortunate. And so we built this massive telescope. And I am now poised to start my university career to carry on this dream of becoming an astronomer. By the time I finish technically in South Africa, my second degree, so this is my second graduation. After my BSc, you do a 4th year of studies if you want to carry on to postgraduate studies. So this is me at that graduation. My parents are incredibly proud. And in the time that I've completed my first stage of my university studies, SALT, the Southern African Large Telescope, pictured here, or the outside of it pictured here on the left, is now being built. So another advantage that I have along the way here is not just my ideas and my parents' ideas and their support, and my family also massively. My family doesn't know what I do. They know I study the stars. They don't get it, but they freaking love it. They're super proud of me. It's all over Facebook. And these are the kind of things that we need to consider when we're really trying to make meaningful and sustainable difference. How do we ignite, the passion in the community? Because my family adores what I do, and they love all this stuff that's happening in my life because of the doors that were opened for me through my education, but they couldn't tell you what I actually studied. The stars, that's all they can tell you after many years of me trying. So another component to my success is the government, the South African government, stepping in and allocating resources. So that's funding for students, funding for facilities, starting the National Astrophysics and Space Science program. While I'm at university, they start this program because they realize they've built this facility now. They need South Africans to actually be trained to do this. So there's another component. I was in the right place at the right time, and I'm not trying to undermine my own hard work, because I was still having to, study and learn, classical mechanics, quantum mechanics, doing all that maths. I was doing the work, but we cannot deny that I was also there at the right time when these things were happening. And now South Africa was starting to look for Black people who were coming up through the ranks. You can see I skip here to studying abroad. I don't have a slide on on the degree I did between studying abroad for my PhD at the University of Southampton and the Harvard-Smithsonian Center for Astrophysics. That was my master's degree, still in Cape Town. It was horrific. I experienced a lot of discrimination, a lot of stress. My mental health is still not fully recovered after over 10 years. And it caused a lot of problems. So I skip over that, but that's actually where I would have really liked the support of people who were, doing EDI and doing social justice work. It would have been incredibly helpful, but it was also incredibly formative. So even though I don't have a slide on it, that degree, my master's degree, was actually probably the place where where that change in me, that kind of radicalized me specifically about social justice in academia. And studying abroad at the University of Southampton, where things in South Africa, everything's very racialized. In the UK and in the rest of Europe, people don't like to talk about race and racism. White people get more upset when they're called racist than I'm allowed to be when I experience racism. So now I'm in the UK, and here the issue is just gender. It's just about women in STEM, getting more girls into science. No, nothing about race, but I am Black and I can't change that. But all of a sudden, I find myself in a very supportive place for women. My year was a very big intake of women. A bunch of us graduated together. It's good optics. Everything's looking great. It's looking like, we're on the right path. We're getting these women in. But what of non-binary people? Never spoken about. What of LGBTQI people? And I'm a member of that community myself. Not spoken about. Interestingly enough, while I'm abroad in the UK, I am very open about being bisexual. I am completely in the closet in South Africa because not ready to have that conversation in the workplace. I returned to South Africa, and astronomy is growing. At this point, South Africa was in the bidding stage or the auditioning stage for hosting the world's biggest science project, which happens to be a radio telescope called the Square Kilometre Array. By the time I returned to South Africa in 2013 as a qualified, PhD qualified astronomer, here's me on my graduation day, wearing the claret and blue robes of Southampton University. South Africa has started building test pilot instruments to show and to convince the SKA committee that we should be awarded the rights to host the world's biggest radio telescope and best radio telescope. So we have this growth of optical astronomy, building these world-class instruments. Now we're getting the radio side as well, again, exploiting South Africa's geographical advantage of these dark skies and open spaces. Although we must remember that these telescopes are built on indigenous land, and there are a lot of indigenous land acknowledgements and consultation with the people of this area to build these telescopes. But again, a massive piece of luck. South Africa, or at least for my career personally, South Africa gets awarded joint hosting rights with Australia to build the SKA. So now there's even more money in South African astronomy, and I get some of that money to do my first postdoctoral fellowship. I'm the first woman of color to be a Square Kilometre Array Africa postdoctoral research fellow. So a very high profile. I experienced a lot of tokenism at this stage of my career. I'm very good for business. I'm very good for optics. I'm fantastic at interviews. I'm very well spoken. I know exactly well, at this point, I don't know the power that I have, but the people who were exploiting me knew the power that I had. And I was literally put on posters and put up at conferences. But at the same time, experiencing a lot of subtle discrimination in my work, and also having my research interrupted because I keep getting emails saying, please come for a photo shoot. And then I would have to leave my X-ray binary work and go to take photos and things like that. And this is something that we call an example of something that I now know is called cultural taxation, where people where racialized or minoritized people are asked to do a lot of extra social justice work in academia without compensation. And it obviously impacts our ability to do research. So at this stage, I'm still doing a lot of outreach. I'm still doing a lot of science communication, but things are starting to shift in my understanding of what actually needs to be done to tackle these problems. So I take up the outreach astronomer job at the South African Astronomical Observatory, the oldest research institute in South Africa, and established as a colonial hub for the British Navy to basically help with their navigation. So this was in the 1800s, early 1800s, to help them colonize the globe. And it's now a fully functioning observatory. And I decided to take up this role as outreach astronomer so that I can build ties with community leaders and make astronomy more accessible for the local Cape Town community. But at the back of my mind, I'm starting to think maybe I should stop doing outreach and actually start fixing the problems inside, because doing outreach started to feel like I was luring vulnerable people into a dangerous situation where they would be bullied, abused, harassed, etc. And I didn't want to do that anymore. Sorry, I know we're running out of time. I've got 2 more slides. So then I leave for abroad again to focus on my research career. I have a Fulbright fellowship in Texas and a Royal Society Newton International Fellowship in Manchester. And it's during this time in Manchester that I start my own company to do my science communication and consulting outside of for non-technical people, like people in the media, policymakers, etc. And this is also where I start my social justice journey, where I take a big step back from doing outreach and putting it into Astrocom so that I can get paid, because I feel that I'm not being compensated enough. And that's one thing that we learn in academia a lot as women in particular, or as minoritized or gender minorities or racial minorities, that there's a lot of work that we do that is not compensated and not recognized, but essential. That's why I started my company to get around that. And now I'm at the University of Amsterdam as a researcher, but I also work for all of Dutch astronomy as the Equity and Inclusion Officer. And this is work that I've put in for myself, self-taught, and I've worked really hard to get to this position now where I can actually affect change through policy and trying to change things from the inside out. So yeah, thank you for your time. I know that was a very long journey, but I just wanted to kind of give you a background to how I got into this position, how excited I am to be here to talk to everyone, and the hard work that lies ahead for equity and inclusion for us in astronomy. Thanks.
Thank you very much for sharing this this talk with us and raising a number of, I think, very important issues that we should definitely consider and try to do something about. We have some time for questions, maybe a bit shorter questions, but if you have a question, please raise your hand and share it with us. Giving everybody a minute to consider. Yeah, I see a question by Alba. Oh, sorry, I have to allow you to unmute yourself, I think. Yeah.
Hi, Tana. Thank you for your talk. It was really nice to see your way towards science. I was wondering, how do you, you talked a lot about how your parents were supportive, and there's something that in my opinion is not that trivial, doesn't happen always, especially for science, something like astrophysics or research in general. So how do you think that was an important factor for you, and how do you feel about other girls, especially girls maybe that don't have this support?
Tana, you're still muted.
Thanks, sorry. I think that my parents' unwavering support throughout my studies and my career is the #1 reason for my success. There's, you know, there wasn't a lot of support from, in fact, the idea that I would have something like, people often ask me about my science role models, like, did you like Carl Sagan? I'd never heard of Carl Sagan till I got to university. I'd never heard of Neil deGrasse Tyson till I got to university. I'd never heard of Richard Feynman. None of these people, even Marie Curie, never heard of these people. Like, I made these decisions in pre-internet South Africa. I knew no scientists, except for the people in the articles that came alongside those Hubble legacy images that were in the newspaper. They would put the Hubble legacy images there and they would write a short article about it. And that's where I figured out that they were scientists who use these images to learn physics. So there was no support when I was in the second last year of my high school career. We were supposed to go do job shadow or work shadow. I tried to go and do a job shadow, ask for job shadow opportunity at the university department, UCT's astronomy department, where I ended up being a master's student and having a horrible time, and then also a postdoc and not being super happy there. And they just basically laughed and said, we don't work with children. So when I was a postdoc there, I ran the outreach job shadow work experience program so that other children could have these experiences, but I had none of them. All I had was my parents standing behind me, like in Dance Moms, or like those people who put their children in pageants. Think of that energy. That's the energy that my parents had to bring to get me through this journey. And so for people who don't have that support, especially young women, especially young women in immigrant communities or in refugee communities where things are stacked against you, you're so focused on, you know, the challenges that the world is throwing to you, never mind academia. It is incredibly difficult. And so we need to take a much more holistic approach to how we do our diversity initiatives. You'll notice I'm an equity and inclusion officer because I believe that diversity will be a natural outcome of equity and inclusion policies. So if you're still trying to do recruitment and drive up diversity in a more direct way, then you need to be more holistic about who you approach. Don't just talk to young women, talk to their parents, talk to the principal of the school, talk to the teachers, because a lot of time the teachers also don't know what the opportunities are. Talk to community leaders and so on. When I was at the Observatory in Cape Town, we had a very good relationship with one of the imams of our local Muslim community. And these are the kind of relationships that we need to kind of forge to get the whole community to see science as something that that community can be involved in.
Thank you very much. Let's thank our speaker again for the very nice talk and new insight. It's fine. I think we haven't really run out of schedule a lot more, and I do think this is an excellent point to actually go into the discussion. I know we're running a bit over time with the event, but I hope that people can still have some time to join us in the discussion. So I would like to invite Akshara to take over again. If she is.
Yeah, I'm still here. Well, we still have a few minutes for some discussion. If you have any more questions for the speaker or general discussion about achieving gender equality in science, please raise your hands, or you can also message on chat, or if there are any questions in YouTube, we'll read it out. Great, we have 3 hands raised. So I think the first one to go is Jan Gerald. If you can. You can unmute yourself if that works.
I think we're several people trying to click the same button, so maybe if only Akshara clicks it.
Okay. I still don't hear you. Jan, can you try unmuting?
Yes, sure. I asked you to unmute now. Does it work?
Great, perfect.
No, it doesn't seem to work, right?
No, I think.
Now maybe.
Yeah,
good.
I hear you. Yes.
Yeah,
perfect.
at some point it said the host, you're not allowing me to unmute myself. Sorry. So it's about your settings.
Okay, sorry for that.
Okay. So actually back to my earlier point that I'm so disappointed in engineering. I'd like to ask an open question on some of the females online here that choose for astronomy, which is of course a beautiful topic to study. And therefore you see that the gender equality is actually not too bad, or diversity is actually quite reasonable, my view then, biased view. Some of the young females, is there a reason? Can you maybe say why didn't you choose for engineering, or is it accidental, or could we do something better?
I would maybe like to say something about that, because I arrived here as a PhD student, but before that I was studying electrical engineering in Delft, which is really, I think the year I started, we had the worst gender ratio in the country. So it wasn't great in that term. But before that, I went into astronomy, and then I did it as a second degree. And I think kind of one of the things that I feel influenced a lot of people was that many of these things are actually very interesting to women and also to other minorities, I think. But the way it's spun by the university is often very much aimed towards like the default student that they already have. Like we had these project courses, and then at some point we found out that there were like half of them were about either building a car or I think building a speaker, building a video game. It's all kind of very much in the stereotypical idea of what a boy who just comes out of high school is doing. So I do think sometimes you need some people to already come in with new ideas and present it better presented in a more appealing way to a minority in such a field?
I think I would like to quickly contribute something to the discussion as well. So I was also an engineer from my bachelor's, and I think what I experienced is completely different because I did my bachelor's in India and we were sort of 50-50 in my engineering course, to be honest. But even if the ratio is still like raising, or like the number of women in your classroom is less, it's still, I hope it still doesn't bother women, and we probably encourage that more instead of stereotyping it that, you know, that you're just a woman in a world of men there. So, okay, so I think Julia also raised their hands.
Can you hear me?
Yes.
Okay, honestly, it wasn't really a question. I just wanted to thank you, like the speakers and the people that made this possible, because like I really feel that in my university we're lacking sometimes role models and female role models, and this was like really inspiring, and I really enjoyed it. I really liked it, and I'm really happy we had this. That's it. So thank you a lot.
Thank you. So do we have any more raise of hands for questions? Stephanie?
Yes, I actually have a question that was kind of inspired by the last talk. Because you mentioned at some point that the idea of a minority that's not really a minority. It's like a discriminated majority quite often. And you mentioned like that would change your strategy. And I was wondering, because you're now kind of entering this these positions where you can actually implement such strategies, I was wondering what ideas you had about like how that would differ.
So this was for me? Yeah. Okay. So I'm currently working here in the Netherlands on astronomy in the Netherlands, and I've not been invited to, except to give one talk about decolonization, which was met with pretty much silence from the establishment in South Africa. I've not been invited to talk to them about these, very much to talk about EDI, a couple of, like I said, decolonization talks. So my ideas that are different is just how we, the things that would be different is how we, the messaging. So the policies would be roughly the same. I mean, the issues are global issues, right? Like between the global north, the global south, east and west, etc. The issues are the same. There's discrimination, harassment, bad behavior that are pushing, they're pushing people out. I'm going to use the term previously excluded or historically excluded groups, because that encompasses everyone and is actually a more accurate description of what's happening. It's not that people weren't interested. It's not that certain people weren't interested, is that certain people weren't given opportunities, and then that becomes an entrenched thing, and there's this feedback cycle, and we need to break that. And in South Africa, the approach would be more from the racialized front, which is what they would expect, but we also need to kind of use it as a jumping off point. In the Netherlands and in Europe, there's a lot of focus on gender, and using that as a starting off point, but then expanding from there. So kind of meeting people with where they are and what they expect, but then expanding to a much more intersectional approach. And I think that in the cases of what's happening, for instance, in Africa with astronomy and the growth of the square kilometer array across Africa, there's this big push now to do a lot more astronomy across the continent. And it's not the only science, there's a lot of other sciences as well that are experiencing a big push. But this idea of how to handle race varies even from country to country. South Africa is extremely racialized because of our history of colonialism and our specific history of apartheid, which is still so recent, whereas in other African countries, they their approach to race is very, very different. Because everyone there is Black, race is weird to them. So these are the kind of nuances that we have to that we have to tease out and be aware of when we implement our plans. The language that we use is so powerful and so important, but the underlying goals that we're trying to achieve, so the goals are the same, but how we get there is going to look different and sound different and feel different. And so there's the classic thing of thinking globally but acting locally. What do you need in your local context? How do you apply EDI principles to your local context, depending on where you are in the world and how that's going to sound and how that's going to look? And that can't be done without consultation of the local community at every step of the process.
Okay. We have Jan, who's raised his hands.
Yes. So I would also, again, thanks to both speakers, to Tana and Francesca, for these amazing talks. I think it's really inspiring to see it. And I think both of you are doing really important work. The question that I have is especially to both of you, and also like an opinion question. What would be your strongest advice that each individual of us could do in their daily life to further promote gender equality, not only in science, but maybe also in general?
Shall I go first, or Francesca, do you want to?
No, please go ahead.
Okay.
I will follow.
I think for everyone in their daily lives, and this is very true for me as well, is don't be afraid to have uncomfortable conversations. We call this, look, I'm going to be 100% honest with you. A lot of my education when it comes to social justice, that wasn't kind of things from, growing up under apartheid. I didn't have a choice to be radicalized. I always knew that there were problems in the world, systematic, fundamental problems in the world that existed. I couldn't escape that. But a lot of my intersectional, so by intersectional, we mean it's a intersectional, for instance, feminism or intersectional approach is a coin termed by Kimberly Crenshaw in the 90s, where it talks about no one person is just one thing. I'm not just a Black person. I'm also a woman. I also have mental health issues. So I have a disability that impacts how I work and live, etc. I am a bisexual Black woman with who's also depressed. So what we need to do is we need to be intersectional in our approach. No one is one-dimensional. We all contain multitudes, and we need to be we need to kind of look at the world from in a more holistic kind of way, intersectionally, holistically, but also learning and unlearning is going to come up a lot. It's a never-ending process. So my advice would be open your mind up, understand that there's no end point, that it's always ongoing, that the language we use has to change. As when we know more, we change how we behave, just like being a scientist or just like being an engineer. You do a thing, you check the outcome, and then you update your understanding based on that outcome, like a Bayesian approach. Bayesian stuff is really hot right now. Let's take a Bayesian approach to our life, learning and unlearning, constantly updating, adding more to how you understand other people, but also understand yourself. Because it took me a very long time, for instance, to come and be open about the fact that I have a disability when I have depression. I didn't want to think of myself as a disabled person, and I still struggle with that aspect of my life. But that is what I am. And people are like, I don't want to put labels on stuff, but sometimes you need to, in order to change something or to be at peace with yourself, you need to acknowledge and name a thing that happens. So these are the kind of uncomfortable things that you're going to have to get used to. Who are you? How do you fit in the world? How do other people fit in your world? What is your worldview? Learning and unlearning constantly.
Yes,
thank you very much.
And I mean, there is very little that I can add after what Tana just said. I think that I fully agree with her. And it's really, as I said before in my talk, I mean, to get out of your comfort zone. It's not always easy. It's, it's not something that comes in a kind of spontaneous way. I mean, we all feel sometimes, in an awkward situation to say something. But I think that you have to pick your battle in a sense, right? I mean, there are different aspects that we can work on and that we can try to improve. And this can be also overwhelming, if you wish, right? Because sometimes you feel that you're making so little progress that, you know, we are scientists, and as scientists, we like to solve problems. We solve them, so we see a result coming out of our problem solution, in a sense, right? It can be a paper, can be solving a mathematical issue, I mean, whatever. In this field, any little step can help, but of course it happens, it's mirrored out on a very long baseline time scale, let's say. So just speak up, don't be afraid. As I said, I mean, now I start, you know, when I see that a panel, usually I look a lot about gender, but not because I don't care about the other aspects, because for the other aspects, we are way far away. I mean, in order to claim any, that we have invested enough, right, into that. So for gender, for instance, I mean, we have been talking about this, right, to have more equal and more balanced committees, and here and there are more balanced speakers, invited speakers. And we are still, like, sometimes you look at some programs where you just say, gosh, I refuse to go. I really refuse to go. I really raise the issue and say, I will not sit on these panels because I am the only woman out of 7 or 8 members. But you need to have the courage just to say. And sometimes, you know, just to say such a sentence triggers something in the others. But of course, they gave it for free because the situation has always been that one. And then they don't question anymore. So you need to push, but also other people start to question. If you are already very sensibilized to these topics. I mean, this is what I'm saying. This is why I said all can help. Everybody can engage and help in making a better world, a better environment, a better, you know, working environment as well. We spend the most of our lives in working, right? I mean, so let's be fair. So, and sometimes it takes so little. I mean, it's just a question raised at the right time, in the right audience, just to make people think.
Okay, very good points. Thank you very much to both of you.
Great. So this is more of a discussion. So if people have anything to say, you can feel free to jump in by raising hands, so we can just unmute you. I also want to say we are bleeding into 15:00, so if people want to leave, you can also leave. And if people have any questions still or contributions to the discussion, please keep it going.
So if I may, I would just like to, I was not fast enough to respond before to Jan and his question about why we did not choose engineering, for instance, right? So it never crossed my mind. I mean, I'm very honest. I decided to do astronomy. I mean, when I was 13 years old, we did astronomical geography in the 8th grade, and that was it for me. And indeed, I had the support of some family members who were also passionate about that, and it helped. But what actually hit my mind while we were talking was the fact that a lot of astronomers come with a degree in physics, sometimes not even in astronomy. Astronomy comes, let's say, the first degrees are in physics, and then maybe they do a master or even the PhD only in astronomy or astrophysics, and physics is one actually of a school subject. So in a sense, compared to engineering, I think that, for instance, in my times, we did not have labs for physics in school. It was really, I would say now, I would consider a rather boring textbook. We were just learning basically theory, but it had so many implications. It triggers so much curiosity. And maybe the fact that there is no a similar subject in engineering where people can try out to build something, right? I mean, the ones who are more passionate about building and thinking about how to improve certain aspects of, I mean, whatever it can be, technical stuff, or can be buildings, can be telescopes, or can be accelerators, whatever you think about it. I mean, as an engineer, software engineer as well. I think, yes, there is a bit of informatics, but it's probably less, significantly less than physics. And that I never thought about that, and I do not know what could be the impact then on people choosing. So in a sense, maybe then engineering is attracting only those who are already, you know, their mind is already set on doing engineering, and is not able to attract new minds who may be a little bit more open still, not so focused on a specific faculty, let's say, or research area. And that may be the difference. While physics, I mean, they are significantly more familiar with, just because of high school having dealt with different aspects of physics and different branches of physics as well.
Interesting comment, Francesca. Yeah, makes sense. And also it relates a bit to the comment that Stephanie made, that she said, well, some of these courses at Delft University are aimed at fixing a bicycle or doing something with cars or something. Male things that, because at the age of 4, you give a car to the kid of 4 and you give something else to the lady. And that's also your comment. How many generations does this need to go before we getting somewhere? Well, maybe multiple generations, and starting very young.
Yeah, even younger than 4, I would say. Unfortunately, I mean, this split brain, you know, and the pink and the blue. I mean, it's terrible, absolutely terrible. Yeah. I mean, it's also the textbooks, right? I mean, that I know that I'm working with a professor in Lund, and they have been carrying out all this research and trying to sensibilize the community in changing the textbooks. I mean, the textbooks are extremely gendered, very gender. You know, I mean, if you find a picture of a female, sometimes is, you know, like a little dancer who does a pirouette, I mean, on something, I mean, in physics, just to explain certain phenomenon of the mirror effect or whatever. I mean, it's a lot of apparat and, you know, technology and all male. I mean, if you Google it, right? I mean, if you just Google for, you know, famous astronomers, what you get on Google? I mean, you get only almost photos of male. And engineering, I did not try. I will try now because I'm curious, but I think that probably, I mean, it will come out exactly the same. And therefore, I think that this effort has to be put in at a certain point. So we need to train also the teachers and change the textbooks, because the textbooks, still my children today, I mean, they still have quite some cartoons about the gender split, who should take care of household and who should take care actually of having a job outside the house. And I find that absolutely unacceptable nowadays, not to mention all the other diversity aspects, right? I think that we are changing, we are moving forward. I've seen more and more that comes in, different aspects of diversity and inclusion, but at a very slow pace.
So I see Veronica has raised her hand.
This is a slightly different topic. And forgive me if this was mentioned. I had a meeting right in the middle of Tana's talk, so I had to go and come back. But I do a lot of outreach for children in astronomy. I do focus generally on trying to find girls to talk to, but I would like to expand to also, as you say, historically marginalized communities, historically excluded communities. And I wanted to know if you had input on how best to reach them, to find them. Yes. Yeah.
So that was for me?
I think so. Or anybody.
Working with historically excluded communities, I think the nothing about us without us is the should be kind of what guides your work and your praxis. And that's obviously, you know, I don't know which group came up with that, possibly disabled people, but it applies to everyone, whether it's racialized people, disabled people, religious people, whoever you're trying to reach. And bring into the fold, consult with them first. It's not, you know, it's not for me to, I'm not a religious person, even though I was raised religiously. And I know that in Africa, again, for example, the way that the global North, for instance, has this tension between religion and science. Does religion have a place in science? And can you be a good scientist if you are religious? In Africa, we don't have that friction. We are extremely religious, and not always Christian. There's a large Muslim community across the continent, and that's got nothing to do with you doing science as your job. So it's very important that you know the local context, and know the cultural backgrounds, etc., of whoever it is that you are trying to engage with. And the best way to do that is to approach them, and in science communication, we call it the deficit model. Don't come in there with that deficit model mindset where it's, you're going to teach people things and it's your job to talk at them. You come in, I guess, humbly and with an open mind, and you talk to community leaders or people, at grassroots level, and you build up from there, because often what you'll find is that there's already people doing that work. They maybe just don't have your platform. And so using your platform responsibly and decentering yourself, because not everyone is the right person for every single job. And we need to also bear that in mind. There might be someone else that for whatever reason is better suited and will have a better relationship with the people that you're trying to reach. And you need to be, I think humility is a big thing that we all need, especially as STEM practitioners. We need to incorporate into the work that we do as well.
Okay, so I see a comment by Tora on the comments section on the chat. To some extent, I think the more pure and conceptual sciences might be considered more acceptable for women, while the more practical and applied engineering and computer science is less acceptable. If we have any response or discussion following that.
I have a thought. Sorry, I feel like I'm talking a lot. Does anyone else have a
comment? No, please go ahead.
I think that I've never heard this this kind of line drawn between conceptual and practical. The way I've seen it, and that makes sense to me, is that the thing is that women are socialized to be nurturers and carers, and so when it comes to STEM stuff, it follows those similar lines. So that's why there's a lot of women in biosciences, in life sciences. They have loads of women at all levels, and at the undergraduate levels, they often outnumber the men significantly. Same with nursing. Nursing is a women thing because it's seen as a woman thing, because you take care. The doctor comes in, the man doctor comes in and knows all the stuff, and the nurse comes and washes you and checks your meds and asks you if you're okay. And it's the same in science. So women are seen to be liking things that working with nature and things that grow and living organisms, and then the men do, we count photons and we do nuclear stuff and we write all the code. And so that's the split that I've seen, and the numbers do tend to bear that out in terms of at least the binary gender split. And we also need to be careful about not entrenching that binary gender aspect when we do our work as well. We need to be, open to people with gender minorities as well. When we start doing this research and going forward, we need to build that into our work. It's not just women and girls that need this extra support in terms of gendered analysis.
I think that was a very, very good comment. So just to keep the same discussion going on, I will unmute Tora, and then I will get back to Julia because I see both your hands raised.
Yes, I was just kind of as a kind of example of that. Like in high school, I went to a specific science class, like very specialized science class, and then in my second year, I opened up for the option that you could kind of like take an extra course at university, and you could, and instead of just like the normal one that I usually did, that was kind of like trying out different things in science. There was also, you could take a bit that was engineering specific, and they divided us into two classes based on what we chose. And the one that was for engineering ended up being almost everything. It was only guys that chose that, even though the entire class was pretty even gender balanced. And then there was also the option of choosing between physics and biology at a later point. And then like the biology class ended up being pure, almost just women, while like the physics class, it was me and like three other girls in the class that chose physics. So it's, yeah, that's see a lot of that.
I think both those issues are a problem of gender equality, that there is a lack of men in biology and then there's a lack of women in engineering. So like, please feel free to jump in, the men in the room, please. But before that, I will get to Julia. I can unmute you. Yes.
So I think my question actually connects quite a lot to what is being said right now. So like when I was in high school in Italy, I often found myself complaining to my parents or my teachers or like adults in general in my life about the fact that we didn't have many female professors teaching science, actually like almost none. And often the response that I had from these adults were, oh, it's because naturally women produce hormones that make them have a deeper connection with other human beings, so they tend to teach more humanities or, you know, like those type of subjects, while men don't produce these hormones, so they're more cynic and they go for science related stuff. And I always felt like it was really not satisfying answer, and it felt really like sexual, no, yeah, like I wasn't really happy with this, but I never knew how I could reply to it, because I'm aware there is physical differences between men and women, but like I don't really know how to like respond to like this type of answer. I don't know if my question is clear. Like I'd like suggestions how I can address this issue when they bring up, you know, physical differences between men and women.
Not easy to answer. Also because usually when you find yourself under the spot, exactly when they tell you, sometimes you don't have really the prompt answer to give immediately, just to, you know, to shut them up with this type of comments. I think that one way that I would answer to them would be, well, it's a pity because you are going to miss actually on, you know, on a huge contribution, or anyway on the contribution of a certain part of a population who could help solving issues and problems, scientific problems. I think that would be probably the fairest and safest also answer. I mean, without really fighting them back with such a comment. Yeah. Difficult. I mean, I'm still surprised that I was also raised in Italy. I lived in Italy. I'm Italian, and I mean, you know, I must say that when I was going to high school, I did not have this type of situations, and it seems even strange, right? Because I mean, it was really significantly before your time, and the society was significantly closer and less open and broaden about EDI matters. I mean, who was talking about that back then? Apart from the feministic, of course, feminism and movement and so on, that women had the right to have a job and not carrying at home. Of course, I mean, that was very evident and very visible. But in our normal life, in school, for instance, I mean, I never heard about these topics being discussed. I never had a problem. I had a female teacher in science, in physics, but I don't think, if I think about her, it's not that she really. I don't think that she made such a huge difference, because I came in already with very clear ideas. But I never felt discriminated, not even during my studies, and I consider myself very lucky about that. I could have got even closer to these issues much earlier than 20 years ago if I would have been discriminated, that's for sure. And then at a certain point, you just decide, as I said before, you think about what is not working, and comments that you receive here and there on the working place at work, you know, I mean, they make you think sometimes, and then you realize that things are not, if you look a little bit more closely, because we are so much focused on what we are doing. I think scientists is a very interesting group of people, because we are so passionate about our science and our research that we are really very focused, and we tend to overlook maybe some social aspects because of that. I've seen many instances, especially when I was in the US, of people working really hard, you know, and spending days and nights at the department doing their PhD, and you don't have time, like, almost to reflect on the rest, just to raise your eyes and look around who is surrounding you. And I think this is fundamental. Yeah, I will stop here.
Great. So do we have any more questions or comments to continue the discussions? Last call. Okay, I don't see any raised hands. So I would like to thank all the 4 speakers who were present today for their scientific talks and their gender equality talks as well. Thank you so much for giving us your presentations on this day for us.
Thank you so much.
Thank you so much for inviting me.
Yes, it was a very nice event and discussion.
Yeah, I hope to hear more from all of you in future on how things are going and how things are changing. And yeah, the organizers have my work email, and I'm happy for you to circulate that. That's why I was hired as the Equity and Inclusion Officer for Dutch Astronomy. So even if you're not in astronomy, even if it's still STEM, I'd like to hear from people if they have ideas, thoughts, feelings, or just want to chat. That includes you, Francesca. I'd love to talk to you.
Sure. Yes,
Thank
indeed.
you,
We should keep in touch. Okay.
Thanks.
Bye. Thank you.
Bye.
Thank you.
Thank you very much. Bye.
Thank you to all the speakers and also to all the attendees for the nice contributions and yeah, thinking with us and discussing these things.
Absolutely.
Thank you.